Welcome to Nexaspaces Tech Education, where we simplify complex tech. In today's episode, we'll explore power supply design, the backbone of every embedded system, and we'll dive into the basics of PCB design, where everything comes together on a real circuit board. Whether you're building an IoT sensor, a smart home device, or your first embedded project, understanding power and PCB design is a must. So let's get started. A power supply is an electrical device that provides the necessary voltage and current to your circuit. Think of it like a heart pumping power instead of blood. Let's break it down. An embedded system like an Arduino or Raspberry Pi typically needs 5V or 3.3V DC. But your source might be a wall adapter, battery, or USB that delivers varying voltages like 12V, 9V, or even 230V AC. The job of the power supply is to convert AC to DC, or change voltage levels. Regulate, provide a stable output, even if input varies. Filter, remove noise and ripple. Protect, prevent overload, short circuit, etc. A well-designed power supply ensures your circuit runs safely and reliably. Power supplies come in various flavors. Let's explore the two main categories. 1. Linear power supplies. Use a transformer, rectifier, and linear regulator like the famous 7805. Simple and low noise. But less efficient, because excess voltage is wasted as heat. 2. Switch mode power supplies, SMPS. Use high-frequency switching to step down or up voltages. Examples: buck boost converters. Much more efficient. Common chips, LM2596, XL4015, etc. 3. Battery power supplies. Use rechargeable or primary batteries. Often include battery management systems, BMS, for charging, protection, and voltage regulation. 4. USB power. Widely used in IoT devices. Typically delivers 5V with current limits, 500 mA, 3A depending on USB type. For embedded systems, choosing the right power supply depends on your voltage/current needs, efficiency, and size. Designing a power supply involves key components working together. Let's walk through them. 1. Transformer, in AC/DC supplies. Steps down 230V AC to lower AC voltage. 2. Bridge rectifier. Converts AC to pulsating DC using 4 diodes. 3. Filter capacitor. Smoothens the DC signal by reducing ripple. 4. Voltage regulator. Maintains a constant output voltage. Linear, 7805, 7812, LM317. Switching, LM2596, MP1584, etc. 5. Inductor, in SMPS. Stores energy and smooths current. 6. Zener diodes. Used in simple shunt regulators or overvoltage protection. 7. Protection devices. Fuses, PTC thermistors, TVS diodes, and current limiting resistors to protect your circuit. Always choose components that support at least 20 to 30% more than your maximum load requirement. When designing a power supply, keep these in mind. Input and output voltage. Load current range. Efficiency requirements. Thermal dissipation. Size constraints. Cost and availability. For example, if your microcontroller needs 3.3V and your source is a 12V adapter, a buck converter is better than a linear one to avoid heating. Also, always check datasheets for current ratings, dropout voltage, in LDOs, and thermal ratings. Let's switch gears into the PCB, printed circuit board, world. A PCB is where your power supply and components physically sit. It connects them using copper traces instead of wires. Key layers. Copper layer, for signal/power routing. Silkscreen, labels and component names. Solder mask, the green, or other colored, coating that prevents shorts. PCB design tools. KiCad, Eagle, EasyEDA, Altium Designer. Basic steps. Schematic design, place and connect components logically. Component placement, arrange components physically on the board. Routing traces, connect the pins with appropriate width. DRC check, verify design rules before generating Gerber files. Export Gerber files, used for manufacturing. Understanding PCB is critical for real-world implementation. Power circuits need careful PCB layout to avoid heat, noise, and voltage drop. PCB design tips for power supplies. Thick power traces. Use wider tracks for high current. Use online calculators to size traces. Short and direct paths. Especially for high-frequency switching circuits. Ground planes. Helps with stability and EMI suppression. Thermal reliefs. Use thermal vias and heat sinks for power-hungry components. Bypass capacitors. Place them near regulators and ICs to reduce noise. Keep feedback traces short. In switch mode regulators, the feedback pin should avoid noisy paths. Good layout equals stable voltage and long component life. So to wrap up, power supply design is foundational for any embedded project. Choose the right type, size components carefully, and ensure proper protection. PCB layout makes a big difference. Plan your traces, ground planes, and thermal paths wisely. In our next video, we'll discuss about sensors and actuators. If you found this useful, like, subscribe, and hit the bell icon. This is NextEd, your guide to embedded systems and IoT. See you in the next one.